So we've just seen what the sun looks like in its interior. We talked about its different layers, the cores, the radiative zone, the convective zone, and then the photosphere, the chromosphere. It's not written here somewhere, it's the next one. Chromosphere, and then the solar wind, right? Okay, all right, so we are going to concentrate now on the core because we do want to talk about the nuclear reaction, thermonuclear reaction that happened at 15 million Kelvin temperature. So here's what happens. We are going to talk about the nuclear fusion in the core of the sun. Okay, here's how all those hot photons are produced. Okay, so first of all, it was the gravity, that shrunk cloud of gas, and with the shrinking it was an increase in kinetic energy and basically heats up. So we have high temperatures. Okay, now these are critical because it's only at high temperatures that the nuclear fusion will happen in the core. So what is fusion? Small nuclei stick together to make a bigger one, and that usually happens in cores of the sun or actually other stars. This is actually what defines a living star. Okay, so as long as fusion happens in a core, we have a living star. What defines a living star? So process of fusion is important. So you said small nuclei, and especially in the core of the sun, that's going to be one proton, or basically the nucleus of one hydrogen atom and another proton here. Proton comes together and forms a heavier, a bigger nucleus. Okay? Now, protons are positively charged particles. Okay? So we have one positively charged and another positively charged, and there is electrostatic repulsion, right? So electric repulsion because you have the same type of charge, right? And that is going to prevent the collision of the nuclei. However, at high speeds, remember speed, high speed, it's high kinetic energy, high temperatures. So at high temperatures, then the nuclei have much higher chance of coming very close together, basically close enough for the nuclear strong force to intervene, which is much stronger than the electric repulsion. So it's going to take over and it's going to bind those nuclei together. All right, so this is what happens in the core of the sun. Specifically, what happens is the so-called hydrogen fusion process. And in a nutshell, so that's just summary of the process. because later on we're gonna see that there are actually 3 steps to it. But this is what gets in. We have 4 protons, which are the nuclei of the hydrogen atoms, and this is what you get out. It's going to be 1 atom of helium and energy, all right, or gamma rays. So the sun releases energy but by fusing 4 hydrogen nuclei into 1 helium nucleus. And here the process happens. As I said, there are 3 steps. Step 1, we have 2 protons, 1, 2. They fuse to make a deuterium nucleus. A deuterium is a nucleus that has 1 neutron and 1 proton. Neutron. All right, so this is a deuterium. Some of the other byproducts of this reaction are a neutrino and a positron. All right, okay. And then you get this deuterium and combine it with another proton. So add another proton, and that step 2 reaction, okay, will produce the so-called helium-3 isotope. So it's not yet an atom of helium-4, the more general one, more stable one actually. This has 1 neutron and 2 protons inside. Okay, now this step also occurs twice, and step 1 also occurs twice, so 1, 2, and then those isotopes of helium-3, they come together and form the final product of helium-4 that has 2 protons and 2 neutrons in its nucleus. And there are some byproducts. Proton 1, proton 2, but there were, so 1, 2, 3, 4, and then 2 more, right? But then two more were produced here. So at the beginning there were 4 protons, right? They come together, and the final product is the helium-4 plus, so there were some here, plus 2 protons, plus 2 protons, and then there were some gamma rays, and if you remember, plus 2 neutrinos. Actually, this is the symbol for them, and plus 2 positrons. These ones. Let's do that. The positrons. Okay? All right. Another diagram that explains exactly this. So what do we have in? 4 protons. 1, 2, 3, 4. They interact together, and the byproduct or whatever comes out of the reaction is going to be the helium-4 nucleus that has 2 protons plus 2 neutrons in its nucleus. And then we have the gamma rays, 2 positrons, and then the neutrinos. Okay, now the most important thing here is that the total mass of the out products is lower than the mass of the in products by 0.7%. But because there is a lot of hydrogen that goes through this reaction, it turns out that we end up with 4 million tons of matter that turn into energy. How is the matter turning into energy? The mass goes to energy by Einstein's relation, mc squared. And c is the speed of light. So this is the energy that is produced. This is where it's coming from, those gamma rays. Okay, so now here's a question. What do you think would happen if inside the sun there's a slight rise in the core temperature? That obviously is going to lead to a rapid rise in fusion energy, right? So we have higher temperature, that means, higher likelihood for proton reaction to happen. Okay, so that means there's going to be more energy, that is the gamma rays, produced. Okay, so basically a rapid increase in fusion energy. Okay, what do you think is going to happen? What's going to happen is the core would expand, and because of that expansion, the pressure goes down and is going to cool. All that core, the core is going to cool. Now, this is a very important, as it basically establishes the solar thermostat. So let me guide you through what happens inside the solar core. So say there is a slight increase in temperature, so T increases. What's going to happen? Then we're going to have more nuclear fusion reaction happening, and that means they produce more gamma ray energy. Okay, well, that is going to cause an expansion of the core. But the expansion means lower the pressure. And if the pressure lowers, then the temperature will go back down. So you see, it's kind of like internally the sun knows what to do. Let's think about another scenario. Say there is a slight drop in temperature. So maybe the temperature went too low. What's going to happen? Well, the temperature is not going to be high enough. So T not high enough for the fusion to happen. So that means not too much, or basically less gamma rays will be produced. And that means the core is not going to not able to keep up with inward push by gravity. So it's going to shrink. And if it shrinks, it's going to increase the pressure. Pressure goes up. And if the pressure goes up, then the temperature goes up to maybe where it needed to be. If the temperature goes too much up, then the other side of the thermostat is going to work towards establishing that equilibrium. Pretty neat, isn't it? So now, how do we know actually what is happening inside the sun? Is this just dreams of a scientist? Well, it turns out the scientists are able to model mathematically, to put together some scientific models of possibilities, and it turns out we refine all those models until they very much agree with what we observe. Okay, so what is this photograph? Shows the mottled appearance of the sun's photosphere, right? So you see the bright spots, each about 1,000 kilometers across. They correspond to the rising plumes of hot gas from the layer underneath the photosphere, which is what we see with our eyes. But don't look at the sun without a solar telescope, right? And the layer under the photosphere was the convection layer with the convection cells, right? So that's where you have the rising plumes of hot gas, and then these are going to be regions where cool gas descends. All right, so these are models, and the models become better and better. You get higher and higher resolution every year. This is actually a pretty old model. Nowadays we're really able to model this kind of motion of the plasma particles on the surface. So yeah, pretty good agreement between the models, which is what we think happens, with what we actually observe on the surface. All right. And then there's another way in which we can probe the solar interior. Remember, there are neutrinos that are created during the fusion that fly directly through the sun. Those neutrinos, they don't interact much with the rest of the sun, for sure. They generally don't interact much. Anyway, there are kind of like trillions going through you every second. So just so you know, this universe is full of neutrinos. So we definitely wanted to observe and measure, count them. Observations of these solar neutrinos can actually tell us what's happening in the core, whether they are produced by these fusion reaction of protons or hydrogen nuclei into the helium-4 nucleus, and the byproducts of gamma rays, neutrinos. Those are the neutrinos, okay, and then the positron. So basically quantifying, just trying to measure and count all these byproducts, right, that would be a good sign, that a good test of what we think happens inside the. So there has been a so-called solar neutrino problem for quite a long time, because early searches for the solar neutrinos failed to find a predicted number, right? So you have the reaction, you know how many are produced, and then you look for them towards the sun and you don't find as many. But more recent observations find that the right number of neutrinos actually is there. But you also found, because nuclear physicists learned a lot more about neutrinos, we found that they actually changed form. So there are different types of neutrinos, and they go from one type into another. How do we detect those neutrinos? I told you they don't interact much with matter. With neutrino observatories like the Sudbury Neutrino Observatory, which you see in this photograph that shows the main tank of this neutrino observatory that's located in Canada at the bottom of a mine shaft that's more than 2 kilometers underground. Okay, and what you see here, it's a large sphere about 12 meters in diameter, right? Diameter 12 meters. So it's pretty large, right? And that contains about 1,000 tons of heavy water. So remember, water, that is H2O, that's hydrogen and oxygen, but the heavy water has deuterium instead of hydrogen. So this is deuterium, which it's going to make each molecule much heavier than the molecule of ordinary water. So anyway, neutrinos of all three types, there are three different types of neutrinos, and they have been recorded. They basically, with observatories like this, we were able to detect all of them. So yes, we got another support for what we already what our model said it's happening in the center of the sun.